Hi, welcome back to my channel, and for today's video, we will be continuing with the isomorphism on linear transformation. So this is going to be the part 3. Okay, thank you so much for all your support, and for those who are new to my channel, please don't forget to subscribe so that you'll be updated on a lot of videos that I'll be uploading soon. Okay, last video, we have proven a theorem at which when f is isomorphism, it implies that the dimension of the v is equal to the dimension of w. So in this case, v and w here are vector spaces, and that f as an isomorphism is a mapping from v to w. So in this video, we are gonna answer the question if it's possible that if the dimension of v is equal to the dimension of w, would it also imply that f is automatically an isomorphism? Okay, so we will answer that by this lemma. Okay, so given that we have a mapping f from v to w, and this is a linear transformation mapping, and then suppose that v is finite dimensional, and the dimension of v equals the dimension of w. Okay, so the following are equivalent. Number 1, f is on 2. Let's start with f is an iso first, because this is our actually the goal. Number 2, f is 1 to 1. And number 3, f is on 2. Okay, so this lemma would answer now the question that given that the dimension of v and w are equal, would it imply that f is automatically isomorphism? So this is now the question, the answer of the question there. So the assumption is they are equal, and another assumption is it should be that v is finite dimensional. Now if it's finite dimensional and the dimension of v and w are equal, then we can jump into conclusion that f is an isomorphism if and only if either f is 1 to 1 or f is on 2. So it's only one requirement, that either f is 1 to 1 or f is on 2, then automatically f is an isomorphism. If you lack with these criteria, that v is finite dimensional and dimension of v and w are not equal, then we just go to the basic. We need to comply that f is 1 to 1 or on 2 just for us to prove that f is iso, because that's the formal definition. But in this case, this lemma is powerful in the sense that you only need to get either 1 to 1 or on 2, and then you would jump into conclusion. But of course, the criteria is that the dimension of v and w are equal, and then v is finite dimensional. So just remember that keywords. So in order for us to prove this, because they are equivalent, so we can just prove 1 implies 2, and then we can also prove 2 implies 3, and then we can prove 3 implies 1. Okay, so it's actually a cycle here. So they are all equivalent. Okay, so the idea that 1 implies 2, so f is isomorphism, then f is 1 to 1. This is pretty obvious by the definition of isomorphism. So there's no need for us to do an effort on proving that, because that's pretty obvious. Okay, so we will prove 2 implies 3. So assuming that f is 1 to 1, so if f is 1 to 1, then the nullity of f is 0. So we've proven this on a previous video about the isomorphisms on linear transformation. Now, the nullity of f is 0. This implies that the dimension of v is equal to the rank of f. Of course. And then, if you notice, the image of f is always a subset of w, and rank of f is equal to dimension of w. Okay, so this simply tells us that the image of f equals w in this case. Okay, so this implies that f is onto. So this is the definition, remember, on the previous theorem that we've discussed on the previous video. So the image of f is equal to w implies that f is onto. That's it. Now we will show that 3 implies 1. So that means we start with the idea that f is onto, then we will jump in the conclusion that f is an isomorphism. So what happened when f is onto? So when f is onto, the rank of f is equal to the dimension of w. So this simply tells that if the dimension of v equals dimension of w, this implies that the nullity of f is 0, implying that since the nullity of f is 0, f here is 1 to 1. So since we've assumed that f is onto and it's 1 to 1, automatically f is isomorphism by the definition of isomorphism. That's it. So we have proven the claim on this lemma. So since this is true, because we have a proof for this, then simply the fact that either an isomorphism is a 1-to-1 or onto, as long as you have a finite dimensional domain, and then the dimension of the domain is equal to the dimension of the codomain, automatically f is an isomorphism. In fact, that's a necessary and sufficient condition. That's it. Okay, so we will introduce another theorem here. This is the last theorem for this isomorphism on linear transformation. Given that you have a vector space V over a field F, if the dimension of V is n, then V is isomorphic to F to the n. So that means if it's isomorphic, then there is an isomorphism that maps from V to the Fn. Okay, that's the idea there. So let's prove this. Okay, let this be a basis. So we will take the basis first. Okay, so if you notice, the number of elements on the basis, on the set of bases, are actually n. It's because the dimension of V is actually n. So, if we assume this set to be the basis for V, then let V, the small v, be in the big B. So what's the meaning of this? Since V is an element of the vector space V and we have these bases, now we can write a linear combination for that. So in this case, there exists scalars. So your scalars, remember your V is over a field F. So the scalars is coming from F. Such that the elements of V, remember the elements of V is a vector. So this vector can be written as a linear combination of this. Okay. So if you have any questions or clarification, you can comment down there about this, how it's being constructed. So let's define now the mapping. So define the mapping F from V to Fn. We define that by sending an element of the domain V, which is equal to this. So this is an element of Fn. Okay, so we will claim first that this mapping is a linear transformation. Okay, so first claim. Let's label this as claim 1. F is a linear transformation. Okay, so if F is a linear transformation, we will assume two elements from V. So let X, Y be in V. Okay, there exists BI and CI in F. So in this case, your I is coming from 1 to N. And then in that case, you can write X, which is an element of B. Remember, V is a vector space, and it's an n-dimensional vector space. So meaning I can write the element on the vector space as a linear combination. So this is the reason why I have this one here, BI and CI. So in this case, I have BI, VI, I from 1 to N. So it's up until N only because V is an n-dimensional vector space. Similarly, for Y, I have CI, VI, and it's I from 1 to N also. Okay, thus, let's check the linearity. So X plus Y. So this becomes the summation, the F is equal to the summation of VI, VI, I from 1 to N plus this one, summation of CI, VI, I from 1 to N. Remember, they have the same index. So property of summation, I can have this instead. BI plus CI, this is VI and I from 1 to N. Okay, and I can have this F here, this summation, I can have B1 plus C1. If I am going to expand this, I would have this one here up until Bn plus Cn Vn. Okay, here's what I'm gonna do. The mapping, if you can notice, the mapping of your F here, if you have an input of V, then this is the output, provided that your V can be written as a linear combination of AI, VI, I from 1 to N. So same with that. This one, I have B1 plus C1, comma, B2 plus C2, comma, up until Bn plus Cn. So it's an n tuple. Okay. I can separate them, by the way. I have B1, comma, B2 up until Bn, and then I have C1, comma, C2 up until Cn. So if you notice, if you are actually adding these vectors here, so you are only adding entry-wise. So the first coordinate, so B1 will be added to C1, which is the first or the second vector, and so with the other orders. And this is equivalent to f of x, and this is equivalent to f of y. So therefore, we have shown that f of x plus y is equal to f of x plus f of y. Okay, so let's check the condition 2 for linear transformation. So let R be in F. Okay, because of course V is a vector space over the field F. So RV, this can be written as R times the summation of AI, VI, I from 1 to N, and this is equal to the summation of RAI, VI, I from 1 to N. Okay, what is that? Why I am doing this? I'm doing this in the sense that I need to show this. My goal here is to see if this is equivalent. Okay, so that's my goal. Okay, f of RV, F of RV, this is already my RV here. So I would have F of the summation of R of, I'm sorry, here, R dot AI VI I from 1 to N. And then what's the output for this F? This is only the output. So I have R of A1, R of A2, up until R of AN. And this is equivalent to, I can extract R, I can factor out R. So I have R A1 up until AN. And what is this? Your R, and this is in exactly the sum of, oh, I'm sorry, instead of writing that sum, it automatically uses as F of V. That's it. So we have shown that F here is a linear transformation. So the next problem is we will have to show that F is an isomorphism. Okay, note that the dimension of V, the dimension of F, N, if you notice the dimension of V is N, the dimension of Fn of course is N. So by lemma that we've shown that before, it suffices to show that F is 1 to 1. So what happened? Suppose V is equal to the summation of AI VI I from 1 to N, and in this case this is kernel of F. Okay, this is an element of the kernel of F. So meaning F of V is 0. So I can write that as A1 up until AN, but this is technically the 0 vector. Okay. Okay, so this implies that all AI is 0 for every I which is less than or equal to N but greater than or equal to 1. Okay, so what does it entails? Since AI is 0, V here is the summation of 0 VI, I from 1 to N, and that's technically 0 V, because that's the 0 vector on the first on the domain. So meaning to say that since V is an element of kernel, automatically the kernel of F is the 0 vector, implying that F is 1 to 1, as we have shown this already from the previous theorem on the previous video. So therefore F is iso. So since F is iso, we can jump into conclusion that V and Fn here is isomorphic. Okay, this would be the last. I'm gonna leave you with a note. Why? If you notice, vector spaces are isomorphic if and only if they have the same dimension. We have shown this already on the lemma. They have the same dimension. Okay, now there is however. Now a linear transformation defined between two vector spaces with the same dimension are not necessarily isomorphic. Okay, so here's the note. The vector spaces are isomorphic if they have the same dimension, but the linear transformation between two vector spaces with the same dimension are not necessarily isomorphic. So I'm gonna show you an example for that. So if you notice, let's consider an example. R2 and R sub 1 of T. So they have dimension 2 over R. Okay. So, meaning to say that R2 is isomorphic to R1 of T. So, let's consider a mapping here. Let F maps from R2 to R1 of T. So, this is a linear transformation such that your F of 1, 0 is T, and F of 0, 1 is 2T. So if you notice, the image of F is A-T, where A is an element of R. But this is not the same as R1 of T. Why? The elements, what are the elements of R1 of T? These are of the form A0 plus AT. Your A0, A1 is an element of R. So they are not equal, implying that the F is not on 2. So since this is not on 2, F is not an isomorphism. So this is the implication of, this is actually the message of our note here, that the linear transformation between two vector spaces with the same dimension are not necessarily isomorphic. That's it. Okay, so that's all for now. So this is actually the part 3 of the isomorphisms on linear transformation. Thank you so much for watching, guys. So if you have questions or clarification, don't hesitate to comment down there so that I would know, and hopefully I will also be able to provide you additional video for this linear transformation with a lot of examples. So thank you so much, and again, thank you for all your support. Have a great day to you, and bye now.